Hi, my name is HITESH AGARWAL, and today I'll be presenting my final year project on decentralized federated learning. So let's get started. The key idea behind federated learning is to train a machine learning model on user data without the need to transfer the data to cloud servers. However, can you see any problems with this approach? The one very prominent problem is that if the centralized server is hacked in this scenario, which orchestrates the entire process, and that can act as a single point of failure for the entire system. In order to deal with this, a decentralized federated learning scenario was introduced. So in a decentralized setting, each device can communicate only with its neighbors, whereas in a centralized setting, you can see that the centralized server communicates with all devices. The focus of this paper will be the decentralized federated learning scenario. What are some metrics to track decentralized federated learning? The network throughput, the convergence accuracy, and time to convergence. Some factors affecting decentralized federated learning are the number of local steps in decentralized stochastic gradient descent, the communication topology between the nodes, the communication bandwidth of the network, whether model partitioning is used or not, the availability of nodes at any particular point of time, and finally the local computational resources for each node. The key research question we'll be looking into is how communication topology and model partitioning affects the throughput and convergence in decentralized federated learning. Now let's see some literature review in this domain. First very important paper in this area is by Wang et al. The paper is titled Matcha, and the key idea behind it is to communicate over critical links more frequently and less over other links. This paper is basically a direct application of spectral theory. The next key paper was by Marfok et al., which has three particular highlights. First is that they define communication configurations for cross-silo federated learning scenarios. This allows federated learning research to be more realistic. Second is using real-world network topology. So we use various real-world network topologies for modeling network architecture. And the final one is modeling communication latencies. So the communication latencies are defined formally, including the computational delays, queuing delays, and link latencies, etc. Now let's look at the methodology we used in our study. The communication topologies that we compared were the star network, the ring network, and the minimum spanning tree network. As you can see in the figures, the star ring and MST network have been plotted on the AWS North America silos database, and this is how it looks like. For the mixing matrix, we've used an equal weights average. So this means that each neighbor is given an equal importance while taking an average. The next communication topology we used is Matcha, which was earlier introduced in the literature review, where the base node topology is decomposed into matchings, and a different pair of matchings is used for every iteration of stochastic gradient descent. Then another upgradation we did to Matcha was to introduce Matcha clique. Now instead of decomposing the base node topology into matchings, we decompose it into cliques. And we also look into how cliques of size k affect the cycle time and convergence. In model partitioning, basically what happens is that if suppose this is our main node and this is neighbor 1 and this is neighbor 2, now instead of both the neighbors sharing all the parameters in all the layers, it only shares the parameters from certain layers. So as you can see, neighbor 1 just shares layer 2 and layer 4, whereas neighbor 2 shares layer 1, layer 3 and layer 5. Now we've used the federated extended version of the MNIST dataset. Then next we've used two networks, which is the first one is the AWS North America network with 22 nodes, and the second one is the EBO network with 87 nodes. Now what's cycle time? So basically cycle time refers to the time taken for worker I to compute its local weights and receive weights from its in neighbors for round k until the next round starts. So cycle time is inversely proportional to network throughput. So the lower the cycle time, higher the network throughput. In order to calculate cycle time, we need to calculate the communication delay for each silo. Communication delay can be represented by this formula, which is basically an aggregation of the training time, the end-to-end delay, and the time to transfer model between two silos. The experiments we conducted are as follows. Now for the communication topologies, we can see that the y-axis shows the cycle time, the x-axis shows the communication mechanism. Through this plot, we can see that ring takes the least cycle time and hence is the fastest topology, followed by minimum spanning tree, followed by matcha, and eventually centralized. Next, the convergence in communication topologies. We can see that all communication topologies converge well, and again ring converges the fastest. From the graph, we can see that as the value of k clique increases, there is no clear pattern with the cycle time. Hence, we can conclude that cycle time is invariant of k in matcha clique. Next, we see that when k is greater than 11, there is a sudden drop in accuracy by 20%. So this tells us that bigger cliques can sometimes degrade the performance for federated learning. Next, the cycle time versus number of local steps. From this plot, we can see that the greater number of local steps leads to a higher cycle time. And these two plots show that the higher the number of local steps leads to a faster convergence for the model. Eventually, our model partitioning. From the plot, we can see that model partitioning leads to a lower cycle time, and it also leads to a lower convergence accuracy. So in conclusion, we can see that ring is the fastest communication topology, and matcha k-clique leads to a 10 to 15% accuracy drop with a high value of k, and high number of local steps leads to a faster convergence with 83% accuracy, and finally model partitioning has a lower cycle time. However, it leads to a 10 to 20% accuracy drop. Thank you.